In this video, we're going to look at the physical properties of the period 3 elements. So we're going to classify the elements on the periodic table. We're going to look at the trends in the atomic radii, the melting points, and the first ionisation energies. And we're going to link this to the structure and bonding of all the period 3 elements. So we're going to start off by looking at the groups and the periods of the periodic table. So all of the elements in the same period have the same number of shells. Remember, the periods are the ones which go down, and hydrogen at the top is in the first period. So for example, everything in period 2 will have 2 electron shells, everything in period 3 will have 3 electron shells, and so on. So for example, lithium, beryllium, and boron are all in period 2 of the periodic table, so they're all going to have 2 electron shells. They all have different numbers of electrons within these shells, so for example lithium is 1 on the outer shell, beryllium 2, and boron 3, but all 3 elements only have 2 electron shells. All of the elements in the same group will have the same number of outer electrons. So, for example, all the elements in group 1 will have 1 electron in their outer shell. All of those in group 7 will have 7 electrons in their outer shell. The group numbers are given right at the top of the periodic table. You might see the end group given as group 0 or group 8. So, beryllium, magnesium, and calcium are all in group 2. And all of these elements have got 2 electrons in their outer shell. We can classify the elements on the periodic table into the S block, P block, D block, or F block, depending on which subshell their last electron is filled in. Here you can see the S block elements, including hydrogen and helium, which are also part of S block. This is the P block. The D block is where the transition elements are. And the lanthanides and the actinides make up the F block. We're now going to look at a worked example, so we're going to use the periodic table to determine the electron configuration of phosphorus. So it is in group 5 and period 3. So now we've identified that it is in group 5 and period 3, we can use this to tell us some information about the electron shells. So because it's in period 3, it's going to have 3 electron shells. Because it's in group 5, it means its outer shell is only going to have 5 electrons in. So we know the first 2 shells must be full, and the third shell must have 5 electrons. We also know that because it is in P block, the P shell must be the last one's filled. So it's 1s2, because we know the first shell must be full, 2s2, 2p6, because we know the second shell must be full, and then 3s2, 3p3, because we know there must only be 5 electrons in total, and the P must be last filled. So 2 plus 3 equals 5. So we can therefore write the electron configuration as 1s2, 2s2, 2p6, 3s2, 3p3. We're now going to look at the trends across period 3, starting with the atomic radii. So the atomic radii of period 3 elements decrease as you go across the period. We can see that sodium has got an atomic radius of about 0.19 nanometers, and this decreases as you go across the period to about argon, which is about 0.1 nanometers. This is because as you go across the period, you increase the number of protons in the nucleus of each of these elements. So if the number of protons has been increased, That means there is a greater nuclear charge. Since we have a greater nuclear charge, this means the electrons are going to be pulled closer to the nucleus, so all those shells are pulled closer towards the nucleus. And if those shells are pulled closer towards the nucleus, this means the atomic radii must decrease as you go across the period. So here we can see the electron shells of sodium and chlorine. Sodium has 11 protons, while chlorine has 17 protons. Now both elements, like we said, have got the same number of shells. They've each got 3 electron shells, so there's no change in the amount of shielding. So given that there's no change in the amount of shielding, the only thing affecting the atomic radii is the strength of the nuclear force of attraction. Chlorine has got 6 more protons than sodium has, so its shells are going to be pulled closer towards the nucleus than sodium's are. Which is why we can see that sodium has a bigger atomic radii. So sodium has got an atomic radius of 0.19, chlorine of 0.1. Because of the increased nuclear charge on chlorine, those shells are pulled about 0.09 nanometers closer towards the nucleus. In order to understand the trends across period 3 in terms of their melting points, we have to look at 3 separate groups of elements. So we're going to look at the metals, sodium, magnesium and aluminium separately. We're then going to look at silicon, and then phosphorus, sulfur, chlorine and argon, we'll look at those as a separate category. So you can't explain a linear relationship like we looked at in the atomic radii. Instead we've got to look at 3 separate groups of elements. And we're going to start off by looking at the metals, sodium, magnesium and aluminium. So sodium, magnesium and aluminium are all metals. And the melting point increases as you go across the period as the metallic bonding gets stronger. So out of those 3 metals, sodium has the lowest, then magnesium, with aluminium having the highest melting point. The reason the metallic bonding gets stronger as you go across the period is that you have an increased positive charge. So for example, sodium is a 1+ charge, magnesium a 2+, and aluminium a 3+. You also increase the number of delocalized electrons. So because sodium is a 1+ charge, it has got 1 delocalized electron. Magnesium a 2+ charge, so 2 delocalized electrons, and aluminium a 3+ charge, so 3 delocalized electrons. And you have a smaller ionic radius as you go across the period, therefore there's a smaller distance between the positive nucleus and the negative delocalized electrons. Therefore, all of these 3 factors give a stronger electrostatic force of attraction between the positively charged nucleus and the negative delocalized electrons, therefore a stronger metallic bond, more energy required to break it, therefore a higher melting point. And we can see here an example of this. So we can see that sodium has got a 1+ charge, while aluminium has a 3+ charge. Each sodium ion has got 1 delocalized electron, compared to each aluminium ion having 3 delocalized electrons. And aluminium has a smaller atomic radius compared to that of sodium. Therefore, the metallic bonding is going to be stronger in aluminium than in sodium, so aluminium will have a higher melting point. Now we've looked at the trend in sodium, magnesium and aluminium, we're now going to look at the melting point of silicon. Silicon is a macromolecule. It has a structure very similar to that of diamond, which you'll have covered in GCSE chemistry. So it's essentially a giant covalent structure. So it's a massive network of interconnected atoms, each one having 4 covalent bonds. Now we know that covalent bonds are very strong, which means they require a lot of energy to break. Since silicon is a macromolecule, if you wanted to melt silicon, you would have to break the covalent bonds. There are no intermolecular forces to overcome here. Therefore, to melt it, you've got to break strong covalent bonds, and that would require a lot of energy, hence a high melting point. Now we've looked at why silicon has such a high melting point, we're now going to look at the trends, the melting point of phosphorus, sulfur, chlorine and argon. Phosphorus, sulfur and chlorine are all simple molecular structures. So phosphorus is found as P4, sulfur S8 and chlorine Cl2. As they're all simple molecular or small covalent molecules, they're all held together by van der Waals forces, and this influences their melting and boiling points. And we can see here representations of the structure of phosphorus, sulfur and chlorine. Phosphorus is 4 atoms arranged loosely like this. It's a bit like a triangular based pyramid. Sulfur S8 is a bit like a crown shaped, and chlorine is just 2 atoms joined together with a single covalent bond. As we've said, the melting point will depend on the strength of those van der Waals forces. Now all 3 of these molecules will have low melting points. Van der Waals forces are very weak and they don't require a lot of energy to overcome. So as we saw from the graph, all of these are in the low end of the melting point range, but we need to look at the trend within these 3 molecules. As you increase the number of atoms in a simple molecular structure, you get stronger van der Waals forces. Stronger van der Waals forces means more energy to overcome those, therefore a higher melting point. So we can say that chlorine has got the lowest melting point because it's only got 2 atoms in, then phosphorus, and then sulfur, because sulfur's got the most atoms, therefore the stronger van der Waals forces, therefore more energy is required to overcome those forces in sulfur. Now we've not mentioned argon here, and that's because argon just exists as a monatomic gas. Argon just goes round by itself. So what this means is that it doesn't form any molecules, therefore the only kind of van der Waals forces are between 2 different atoms of argon. Given that it's only 1 atom big, it's going to have the lowest melting point out of all of these simple molecular. Now we don't call argon simple molecular because it's not a molecule, there's only 1 atom in it. So we've now covered the trends across period 3 in terms of the melting points. We've said that the trends across the metals, sodium, magnesium and aluminium, is that as you go across the period, the melting points increase. This is because as you go across, the metallic bonds get stronger, therefore more energy to overcome those electrostatic forces. Silicon has a very high melting point because it's a macromolecule, and in order to melt it, you've got to break those strong covalent bonds, requiring a lot of energy. And for the simple molecular structures, phosphorus, sulfur, chlorine, and then argon, the melting points depend on the number of atoms in their simple molecular structures. So sulfur, S8, has the highest, then phosphorus, P4, then chlorine, Cl2, and finally argon as its monatomic. The final trend we're going to look at is the first ionisation energies. Now in general, the ionisation energies increase as you go across the period. This is because, as you go across the period, the number of protons in the nucleus increases by 1 each time. This means that there is an increased force of attraction between the outer shell and the nucleus. This increased force of attraction means that it's harder to remove an electron from the outer shell because it's experiencing a greater force of attraction from the nucleus, therefore more energy is required to remove that outer electron. Therefore, the ionisation energies increase as you go across the period. You may have noticed, however, that there are 2 elements which don't fit this general increase. Now, these examples will have been covered in your first physical chemistry topic. However, we're going to look at why aluminium doesn't quite fit the pattern of general increase and why sulfur doesn't quite fit that pattern. So if we look at magnesium and aluminium, when we come to remove that electron, in magnesium, we're removing it from a 3s orbital, and in aluminium, we're removing it from a 3p orbital. Now, the 3p orbital is further away from the nucleus than the 3s orbital. So since the 3p orbital is further away, it experiences a lower nuclear force of attraction, Therefore, it's actually easier to remove the 3p electron than the 3s electron, even though aluminium has one more electron than magnesium and a greater nuclear force of attraction. Given that 3p orbital is further away than the 3s of magnesium, it's still easier to remove it, which explains why aluminium has a slightly lower ionisation energy than magnesium. For phosphorus and sulfur, we're removing the electron in phosphorus from the 3p3 orbital and in sulfur from the 3p4 orbital. So if we draw these subshells out, we can see that the electron we're removing from phosphorus is 1 in an orbital with 1 electron in. However, from sulfur, we're removing the electron from an orbital which already has an electron in. So we're removing a paired electron in sulfur compared to an unpaired electron in phosphorus. This paired electron experiences some repulsion, because obviously the spins aren't aligned, they've got opposite spins, which means it's actually easier to remove a paired electron than an unpaired electron. So that explains why sulfur has a slight dip in its ionisation energy compared to that of phosphorus.